Good morning and good afternoon, everyone. A very warm welcome to all of you, and thank you for joining today's webinar. On behalf of DEP, I sincerely appreciate your time and participation, and welcome you all for today's seminar on physics-driven predictive and generative AI to transform product development and manufacturing. As we all know, artificial intelligence is transforming almost every industry. However, in engineering, success depends on more than just data. It requires a deep understanding of engineering physics, simulation, and product behavior. Today's session will showcase how combining physics with AI can help organizations accelerate product development and make design decisions faster. In this webinar, you will also get to see automated feature recognition techniques, some of the features like ribs, holes, fillets. We also see how parameterization can help in creating the database which is required for training the models. And we also see feature-based design generations and many industrial applications. Before we begin the technical session, I would like to briefly introduce DEP and its capabilities and what we bring to the engineering community. This slide provides a quick overview of DEP. DEP is a global engineering solutions and software company with over 25 years of engineering expertise. We have successfully partnered with more than 500 customers across the globe. Our strength lies in combining engineering expertise with proprietary software platforms and AI technologies to help customers accelerate innovation throughout the product development cycle. We support solutions or provide solutions in many areas. Some of the key areas are engineering consultancy, product development, talent acquisition, and all software solutions. Engineering consulting is one of the DEP's core strengths. We support customers from product ideation and concept design all the way through detailed engineering, virtual validation, optimization, and product prototype support. We have been working with many OEMs across the globe in the field of CAD, CAE, CFD, NVH, durability, crash, thermal engineering, systems engineering, electrification, and many other domains, enabling us to provide end-to-end engineering support. Under product development, it's primarily into electromechanical product development team. This team, beyond engineering services, DEP develops complete electromechanical products. Our capabilities include concept generation, mechanical design, electronics integration, prototype development, testing, and product validation. Whether it is electric mobility, industrial products, or smart connected systems, DEP supports the customers from concept to production. And you see the tools like all power, electric power tools, or be it a combustion sensor, there's a drone technology, or improving the engine efficiency. These are all inbuilt products that we have developed in-house. Then another key pillar is on staffing or the talent acquisition team. We provide specialized engineering workforce solutions across multiple domains, including automotive, aerospace, electrification, or embedded systems, and not to mention CAE. This allows us to support customers not only with the technology, but also with highly skilled engineering resources. So we have a pool of engineers whom we place across the industries. And coming to the flagship product, which is MeshWorks. MeshWorks is an integrated CAE platform that helps engineers automate model preparation, meshing, concept modeling, optimization, post-processing, and other workflows. It significantly reduces engineering effort and improves productivity, enabling engineers to focus more on innovation than carrying out repetitive tasks. And if you see here, multiple modules are integrated in Meshworks, right from meshing, where complete meshing and modeling integration can be done. Once integration is done and set up a run for any, any domain, maybe solve crash or durability, run it in third-party solvers, and using post-processor, we do complete post-processing of the results. Once results are being achieved, and then you see it may not be meeting your performance targets, then we use concept modeling tools or to create new concepts or to improve the performance of this. For example, you add a rib or remove a rib, changing the thickness of a rib or the wall of a cast component can be quickly modified or changed in Meshworks. Then we have something, a technology called parameterization. Parameterization, where typically you see parameterizing the CAD models, but whereas in Meshworks, you can parameterize FE model. It can be shape, it can be thickness, it can be material, or even it can be in airbag simulations, the firing time can also be parameterized. You can parameterize welds. You want to define how many spot welds you need, and you parameterize that, and then come back to the optimization. So using that parametric model, you carry out complete multidisciplinary optimization to find out the best lightweight design. Okay, so there's another technology. What we have is CAD and CAE morphing. Here we will be able to morph the legacy models to a new geometry, new shape. So if you have a vehicle which is already in road, and now a new studio room, you get a new theme of with new styling data. Using new styling data, we can morph the existing FE mesh and create new FE model. And one more thing, this come back to the concept modeling. In concept modeling, without really having CAD, if you have a sectional data, you will be able to create complete BAW, body in white, in case of automotive sectors. So you have any section, you'll be using that. You can directly create a 3D model from the sectional data, wherein you are not really using any CAD information. Likewise, there are many modules in Meshworks. Coming to the next key component, so that is, which is today's focus, is on AIWorks. AIWorks is DEP's physics-driven predictive and generative AI platform. It supports engineers across the complete product development life cycle, from concept design and detail engineering to validation. So our technical team will shortly demonstrate these capabilities in greater detail. So this is our global presence. DEP has established a strong global footprint with offices and engineering teams across North America, Europe, and Asia, close to about 13 plus countries where we are present. This global presence enables us to work closely with customers worldwide while providing localized engineering support and leveraging global expertise. These are all some of our customer list. We are proud to work with many of the world's leading OEMs, Tier 1 suppliers, and engineering organizations across the sectors, including automotive, aerospace, energy, and manufacturing sectors. These long-standing customer relationships reflect the trust placed in DEP's engineering capabilities and our commitment to innovation. With that brief introduction to DEP, let us now move to the main focus of today's seminar. Today's session will explore how physics-driven predictive and generative AI to transform the product development and manufacturing is reshaping the product development and manufacturing, and how AI works is enabling engineering teams and design smarter, innovate faster, and significantly reduce development time. It is now my pleasure to invite Mr. Arul Ganeshan and Jashwant, who will take you through the technical presentation and demonstrate the capability of AI works. Arul, over to you. Thank you,
Thanks.
everyone. I hope you enjoy the session and look forward to your questions during Q&A. Thank you. Yeah, please, Arul.
Thanks, Ravi. Thanks for introduction. So let me share my screen. Okay. So again, welcome to everyone. This is the third of a series of webinars on AI Works, which is the AI module for the parent Meshworks software. So by ways of agenda, we will first just recap what we shared in episode 1 and 2, namely AI Works overview and some details on Simulate AI. Then we will get into the core of our topic this morning, this afternoon, which is Features AI. That is one of the 4 modules within AI Works. The benefit of Features AI, of course, is to be able to recognize parts in CAD or mesh, and using that recognition we can apply a customized mesh or apply a customized type of modeling. So the idea is, it helps make your meshing and model building more efficient. We all understand that one of the pain points in the CA world is the time and effort it takes to create a good mesh. So we hope that as you understand the capabilities of Features AI, you will come to appreciate how this can add value to your workflow in whatever type of product development you are in. We'll give some examples, namely clips. So we've done an exercise to show how we can train an AI model to recognize clips and then use that trained model to be able to recognize features, the same features in a new model, and apply custom automation for that, whether it is custom mesh or custom type of connection. However you like to use that recognition, that's up to you. We'll also have a live demo on that. And finally, we want to close out with the question and answer session. So as Ravi pointed out, the parent software is DEP Meshworks. It's an integrated CA platform. It has, as Ravi also reinforced, meshing and post-processing capabilities that are second to none, in some ways better than other available software. But there are some strong modules within Meshworks, as we explained to you earlier: the parameterization, the ROM modeling, concept modeling, and post-processing functions. Our focus today is on the AI Works itself. This parameterization will come back to it in the scope of Features AI. But AI Works is the AI module within Meshworks. In fact, we have branched it out into a separate entity in itself, which we're calling DEP AI Works. Within AI Works, we have 4 sub-modules: Simulate AI, Features AI, Geom AI, Agentic AI. Simulate AI is the ability to have a surrogate model for performance prediction. So we give the CA engineer to take any historical data he may have. He may have solver input data, solver output data for some few designs he has already worked on in the past. So he can take that data and create a model using the library of architectures available within AIWorks, and use that as a quick predictive tool, a quick answer, if you may, to help him give quick feedback to the design engineer. So that's the idea of Simulate AI. Features AI, as we explained, it helps in the meshing process in automatically recognizing some CAD features that may be repeated in your organization, and then using that recognition to apply a custom mesh or to apply a custom type of modeling for that, if it is a fastener, for example. Geom AI takes the output of generative AI, which is in the form of point cloud, and creates practical concept data, whether it's CAD or mesh. So there are tools to help you do that. In agentic AI, we provide an agent that helps in any of the processes using Meshworks. Could be a pre-processing workflow or a post-processing workflow. And the idea is it can take natural language as input and it can execute functions for you. So it takes the manual process in the meshing or the post-processing, recognizing what steps need to be done to complete a task. And if it is stuck at a particular step in the workflow, it knows how to react, what are the decisions it needs to make. So we'll have a seminar on that coming up in another 4 weeks. But that's what agentic AI is about. So a quick recap of what Simulate AI is. Again, it's a surrogate approach to performance prediction. It involves a sequence of steps. It always starts with data. We need decent amount of data to build a model. But if you don't have data, we can help you there by using the parametric capabilities within Meshworks. Take 10 models and make that into 50 models by parameterizing the design and then exporting 10 models for each baseline design. And obviously you run the solver and now you have 50 different designs which capture the variation that you are going to expect and need to help predict for the AI model. So those are supplementary tools to help you make up training data if you don't have sufficient. And then the heart of the AIWorks is the adaptive trainer, where we have a library of architectures, deep learning architectures that are at your fingertips so that you can adapt your particular problem for a particular architecture and use that to create a solid predictive model. This is the workflow. I think it's not new to most people, but you start with data. You have, for example, 50 different STL files of exterior profiles, and you have 50 drag coefficients for each of those profiles. So now you would like to create a predictive model to be able to bring in a new exterior profile. You don't want to run CFD analysis. In a few minutes, you want to predict the drag coefficient. So you take all the 50 profiles and their associated drag coefficient. You use an architecture available in AIWorks, create a model, and then next time the styling engineer provides a surface, you can bring it into AIWorks, click a button, and within a few minutes, you will get your drag coefficient. So that's the idea, and this surrogate approach is becoming more and more popular in the CAE world. And as companies try to speed up their product development process and give the company a competitive edge. So what can we predict using the surrogate approach? We can predict scalars. The example I just talked about was a scalar response where we are predicting a number, a drag coefficient. We can also predict vectors, a force displacement type of curve or an acceleration time curve. So whatever a physics-based solver gives you as a metric for your performance, a surrogate approach can be created. We can also create a surrogate model for uh, contours like a pressure contour, like a velocity contour, etc. We can also create a model for predicting the time history. Suppose you're interested not only in the final displacement and stress profile, you want to see the sequence of deformation steps from the start of loading to the end. We can create a model that gives you all those time steps. Obviously, the memory and the time taken to create such a model will increase because there's more data, but certainly it is doable. If you are using superelement type of analysis where you're representing a submodel in your larger model as a stiffness matrix, we can create a model to predict stiffness matrices as well. Now we just want to give you some background on CNN. Again, I don't want to repeat the first session, but CNN uses the same logic as you would use in an image recognition architecture. Now you pixel an image and you associate a label in the image to the topology of the pixel. And by training it with several images, you can now bring in a new image, and identifying the pixel topology, it will return the label or the number in that. So it's the same idea we are using for performance prediction. For example, drag coefficient. Instead of a 2D voxelization, we are doing a 3D voxelization. We are taking the full volume of the training set, discretizing it as cuboids or voxels, and trying to make a relationship with a particular voxel topology to a associated drag coefficient. And by training these type of data, we can bring in a new exterior profile, and the model will predict the drag coefficient. We've got very good accuracy to the point of 99% with that CNN approach for scalars. A more popular architecture is the graph neural networks, where when data is stored in the form of a graph, you have a nodal XYZ and connected nodes. You can try to make an association between that data and the corresponding nodal output. For example, the node XYZ and the corresponding connected nodes in your mesh, and the pressure at that node can be an output for training. So this is a graph neural networks. It works well because most of our CAE models are in the form of a mesh. So you have a node which has an XYZ coordinate, and you have connected nodes through the elements. Something that we also use quite a bit is physics-informed neural networks, where we are bringing in physics laws in addition to data-driven laws to help guide the training to a more physical satisfying solution. And what I mean is we're not just trying to fit data, we are trying to make sure that the solution matches the physics of the problem as much as we allow it. The other good feature within AIWorks is the ability to give some intelligence to the training. We can force certain nodes to be zero displacement when we know that they are constrained nodes. And when there is an area of interest, like on a hood where the indenter hits the panel, we can focus our training on those areas so that the loss is reduced even further compared to the general area of the hood. We also have good metrics to evaluate a machine learning model. And also we have metrics on how to check if a model that we are going to use an unseen data on is actually a good value. So sometimes we have a machine learning model based on a few specific type of training data, and we want to use that model to predict the response of very generic input data. We know that that's going to be a challenge, but before we even attempt that, we can do what is an equivalence score. It's really a quantification of how a new unseen data fits in with the original training data. The idea is if it fits in well, then we know that the prediction is going to be a good accuracy. If not, we can't expect a good accurate prediction. So there are tools to help you in that. The auto parameterizer helps you parameterize automatically without the investment in time of manual setup. So if your baseline model is not meeting performance and you want to improve the performance, or you just want to do what if studies, you can use this auto parameterization to parameterize your model, and then you can use the optimizer inbuilt algorithm where it uses the design space defined by the parameters of the model, the min and max value, and allows you to optimize for mass or a particular performance criteria. The only difference is it is now using the machine learning model as a solver as opposed to a CFD or a Dyna. So this really speeds up the whole optimization process. What might have taken a week to run can now be accomplished in 5 days, and we have given lots of examples of that in the last two sessions. One of them being this drag coefficient, where you can quickly ask the solver to give me a shape that meets a particular drag coefficient. So you have a well-trained machine learning model and you have a parameterized design, and it will iterate within the min and max ranges of the parameters and arrive at a solution that meets your drag coefficient, and it will provide the value for each parameter. So this is very powerful, and we know organizations that have adapted this type of approach. The Gen AI is the idea where you're not using a model to predict performance of a design. You're specifying the performance that you need, and the model will return a design that matches that performance. So you think about a knuckle that we have lots of data for. We have the stiffness at the interface values. And so when we have 500 or 600 types of data, that's the number of data we need for a Gen AI model. We can train a CGAN architecture, which is a generative architecture, to be able to take in specified performance, and the model will return a point cloud. So it won't give you Nastran data or CAD data, it will give you a point cloud, and we can take the point cloud and create concept mesh with that. So that's the idea of Gen AI. And then to be able to manage all this data, we have a good data connector architecture. When you create a machine learning model once, it's not done. Sometimes you may get new training data, so you can continuously augment your model by adding that to the training, and so you can maintain a good model and keep updating it as training data becomes available. So for that, we provide a good database to be able to manage all that. So the focus of our discussion today is features AI, where we are helping the meshing process using AI modeling, AI models rather. So again, there are three steps: the parameterization, data creation. To be able to train a model to recognize certain CAD or mesh features, we need a lot of data. And sometimes you may not have sufficient data, so we provide tools for helping with that. One of them is the CAE parameterization that Ravi talked about earlier. Um, Again, the idea is you have a baseline model and you parameterize the critical features or the structural features that impact performance. And from one baseline model, you can create 30 more models without doing any manual remesh, without going back to CAD and creating new CAD designs. Everything can be done in the CA environment. And with the click of a button, you can create a good number of DOE samples. It does require some setup where you have to establish your control nodes, the direction of the motion you want to influence. You have to define the boundary nodes which move along with the control nodes, and then you have to define the constraint nodes which are not moving at all. But once you understand this concept, you can on your own take a design and create a parameter, many parameters, specify a min and max range, and quickly create a DOE for your optimization or other purposes. It can be done at a global level, like you see here and here. This is an example of taking an NVH model, and you want to do some concept studies. You want to play around with the height and track width and the length and so forth. So it can be done fairly easily once you understand how the morph setup is done. But these types of tools help you in early stage concept development to give quick feedback. You may not always have the time to go ask your CAD engineer to redesign and provide new math, and then the time effort spending in remeshing can be huge. The parameterization can be also at a very local level. So local features like ribs, holes, slots, welds, we can parameterize the number of welds very easily. Weld optimization can sometimes be a pain if you're manually changing the position of the welds and the number of the welds. But once you create a spot weld parameter, you can easily go from 100 spot welds to 60 spot welds. It will automatically readjust the length between the welds so that it is a good, nice connection made between two pods. So the idea is in your training for Features AI, where you don't have enough data to train a Features AI model, you may be able to use tools like this where you can add more data to create more features or to change the shape of features, so that even there's a subtle difference in your feature, we train the model to recognize that. And so more the data, the more accurate your Features AI model will be. The another tool that is available for you to augment your training data for Features AI is the concept modeling, again alluded to at the outset by Ravi. So this is the ability where we give the CA user to create his own designs in the absence of CAD. So for example, in a concept design, you have a tie bar and you have a fender, but you don't have a connection between the two. So using tools within ConceptWorks, you can create a line between these two parts and then change the line to mimic a structural member, a continuously flowing structural member. And using additional tools, you can create a link between your tie bar and your fender. You extrude that to create an actual 2D section. So tools like these to help create uh, models when you don't have CAD are particularly useful. And in the context of Features AI, you may need to use these kind of tools to be able to add to your database. Doublers, you want to create a reinforcement. You don't want to lose time to go ask for the CAD engineer to be able to provide you CAD for that. You can take the elements of the parent sheet metal and then create a reinforcement using these lines as shown here. So very powerful tools to help you generally in product development in the concept stage, but also in adding to your training database. Sometimes we are playing around with different concepts for a particular load path. So ConceptWorks can help you in that regard as well. Um, at a local level, you want to add more ribs. So you are able to use ConceptWorks to quickly create a ribs. No need for creating CAD first and then creating a rib. So the idea is we have a tool here that helps you in creating design when CAD is not available, and this can be used for supplementing your training data. So we've talked about the tools to help you with your data creation. Now we go to the training itself. Again, we have a library of architectures that you can use for features AI. So we won't repeat that, but whatever is available for the simulate AI is available for adaptive trainer as well. The feature recognition, how do we use the feature AI machine learning model? So you have trained a model to recognize certain features, and now using that model, you can bring in point cloud data or scan data or STL data from a CAD package, and the machine learning model will recognize certain features that you have trained it for, and what you do with that recognition depends upon you. You may use that recognition to create or apply a customized mesh. Now, sometimes these features are a bit complicated, but very important for the performance of the structure. And people spend a lot of time in having the right element size, having the right number of nodes around the hole. So to avoid that time of manual mesh creation, we are able to use the machine learning model to recognize it and apply a custom mesh as we show here. So we are going to show an example of a clip. A clip is a part that is used quite extensively in plastic assemblies in IPs and interior parts of the vehicle. So we don't want to spend the manual effort of creating the mesh each time. Maybe there are tools within your pre-processing to do that without AI, but with AI, we take it a step further where we are actually allowing for subtle differences, and we recognize those differences and apply a customized mesh. So for example, uh, we have a IP structure where these types of clips are used extensively. So as soon as it recognizes these clips, we can enforce and automate a particular type of modeling for those clips. So we recognize those clips, and then it'll automatically create the type of fastening model that you like for your purposes. If it is perhaps a safety model, maybe rigids are okay. If you're doing more an abacus where you need to account for the preload, maybe you use a contact 3D approach. So whatever you like, as soon as you recognize a feature, you can um, enforce a particular type of model for that. So that's the idea of features AI. And we will give you some more understanding of this through a live demo. So I'm going to pass it on to Jaswant, my colleague, to show a live demo of how this works.
Yeah, thank you, Arul. I will go and share my screen. Okay. So far, as Arul comprised about how Meshworks can utilize for data generation and how AI works can be used for performing various type of surrogate model building and AI model for identifying features, everything. So I'll be showing a quick demo on how we can identify one such. In display, we can see we have multiple features here with us. Toggles, heat stacks, everything. So it will be a tedious task for a user to identify clips among them and further proceed with their task. So what we have done is we have built a AI model which will identify these clip kind of features in a minute. So let me go ahead and select that AI model. Then I'll provide an output directory which will dump the required log files and say find features. Now this AI model will interact with the CAD in the canvas, be it a CAD or a FE data. It will identify the required features that we have selected for. So when I say, we can see it has identified the clips. And if you observe closely, this clips, they are varying in different geometries. So over here, there is this flat and uh, rib in notch, whereas in this region, if you see, the clip is having step and rib is having a different feature. So similarly here, like this, be different kind of clips. If we train a AI model to identify a particular feature, it will get the job done for us. Now the question may arise, what we do with this feature recognition. Now comes the next demo where I have a IP panel like this. And as a user, we know how time consuming and tedious it is for us to connect the clips here. So let me hide this. So we can see there are multiple clips in this model, and it each and every location, if a user has to visit and create a rigid or create a contact, as Arul mentioned, based on different load type, we may need to create different connections. So as such, it will take hours to complete this process. Now, what we have done is we have made use of this features recognition part, and in the interest of time, let me select a small portion. So if you could see, I have selected some of the regions where Dago's clips are there. And what I'm going to do is simply say execute. This AI feature recognition will come in action and identify regions where the clips are present and create rigits only in those regions. You can see, right? Like this, we can build multiple AI model to identify different kind of features and integrate them in our daily workflows to reduce the time from hours to minutes. So imagine this entire IP will take an hour or two to complete. With this tool, we can get it done within 5 minutes. Let me go to the next demo. The next demo will be, we have the point cloud or STL data like this. So we may have input. It can be a point cloud data like this, or it can be a STL data like this. If a user has to convert this STL data into a workable FE, which will take days to be completed. So I will show a portion here how we are using the feature recognition technique to convert or workable FE. Let me select a portion of the scan data, STL data. And if you observe here, I'm selecting randomly. You can see the selection is jagged. Also, if you focus here, the edges are also not defined properly. So with this, user can't use the STL data directly. So we have to do some modification or extract a different kind of mesh from this. So we have built this tool where the feature recognition comes in action, will identify the features such as fillets, holes, flanges, etc. Then separate them and treat them differently and produce a workable mesh. As we can see, we have multiple options here which will enable us to do the or achieve the required function. So this correct holes, what it does is, based on the radius provided by the user, it will identify all the holes within the selection, then create a washer. So let's say I want a washer of 3.5 mm washer width. Then correct flanges, if I check on this option, what it does is it simply will treat the flanges which we saw earlier, having dents and node shootout kind of things. So this will be taken care by simply checking on correct holes and correct flanges. Now comes the quality correction part. When we create a mesh from this STL data or the scan data, it should be a mesh where we can perform analysis. So we have to consider quality aspect as well. based on the input provided by the user uh, in the quality panel, it will take those into consideration and correct the flow accordingly, all while maintaining the features such as fillets, flanges, holes, etc. into consideration and give a workable FE. Now, all I need to do is simply click on scan to FE. All the things I have defined will work in the background, from feature recognition to generating a mesh of a proper quality and giving a output which can be used for a solver run. So it will take a minute or so, less than a minute, and we'll have the portion which we selected converted to the FE. It's almost done. And also there is this one more additional feature where if needs to add some additional feature, if we find that the scan to FE is not giving a proper output or needs to be enhanced further, we can create our very own features and imprint them in the FE as well. So that option is also there. So not only user is generating a mesh from the scan data, user is also controlling how the mesh needs to be there. So we can see, right, this red color lines indicates that the feature identification has happened. And if I turn off this scan data, we can see the flanges are corrected properly and holes are treated according to the washer thickness we provided, and stamped kind of feature also taken into consideration. And starting from here till here, where we selected the FE, we can see even though I have selected a jagged kind of layers, it has nicely identified that and made a FE projected properly. So with this ability, user can easily generate FE from a scan data or a point cloud data. So from point cloud data, we'll detail discuss in our next session. So for now, I will show you the output here. So you can see this is the scan data, and if I hide the scan data, we can see the FE generated, how nicely the FE is generated, taking into consideration all kind of stamping features, holes, slots, everything. And if you observe over here, there are some peaks present in the scan data. It has identified those as well. And if I turn it off, we can see a smooth transition is happening in the flow. So this user can correct it very quickly by our highly automated tools and get the model for ready for the solver run. So imagine using this tool, we can reduce days of work to hours of work. So these are the few examples I would like to present for today. And with this, we'll understand how we are using AI to prepare a model to identify features, and then how we are incorporating it to do a meshing activity or a modeling activity. If even further, if you want, we can do a deck setup as well.